Hello, in this video I want to present a surprising result to a hydrostatic problem. And of course the result itself is interesting, but another objective of the video is to show that we should be very careful when we solve problems in situations we have not solved the exact same problem many times. Because if we use our intuition to take shortcuts to get to an answer, well, we may get the wrong answer. So here is how it goes. We have kind of a J-shaped tube that was initially full of air and in which we poured water. So the water will fill up the tube slowly, and at one point there will be an air bubble trapped, and we keep on pouring water until we reach the top of the tube and we seal the tube. Then, just by moving the tube around, we can move this air bubble, because basically if we can just turn it on this side so that the air bubble comes here, and we turn it back so that the air bubble comes up, and we get to the second setting in which the air bubble has moved from here to here. And the question is, if we look at the pressure at the bottom of the tube in this situation, P1, and in this situation, P2, is the pressure P1 smaller, larger, or equal to P2? And we could say, well, okay, let's think a bit about it without doing all the calculations that are needed. We know that the pressure in a water column is only dependent on the height of the water column, and the higher the water column, the higher the pressure at the bottom. So we could say that, well, here we have a large water column, and here we have a smaller one, and here we only have air, which weighs nothing, and we should expect that P2 would be smaller than P1. So that's one situation. The other thing we could say, well, this is a closed system. How are we going to create the pressure? Where do the force come from? And in this case, we would say, well, since it's a closed system, the pressure here would be equal to the pressure here. And could the pressure be larger? Well, our two previous reasonings state, well, there's no reason why the pressure P2 should be larger than pressure P1. And that's probably not the case we could think about. And of course, you know what, because this is a video with the surprising result, we know that the result will be that P2 is indeed larger than P1. But we have to take a look at why this is the case. And the first thing that this shows is that, well, our intuition gives two different answers. So basically we have one of them at least is wrong, so our intuition is not perfect. And the second one, it shows that when we get into new situations, because here this is an enclosed system with an air bubble, this is different from every problem probably you've seen in hydrostatic, in which we have a container that looks like this, and then there is some pressure, and then sometimes they put a hole and there's water coming out and things like that. We've been solving these kinds of problems for a long time, but this is totally different. And now what we need to do when we get into a new problem that we don't know how to solve, we don't have a pre-established answer to, that only depends on some parameters, we have to go back to first principles and think about what's happening in there. So the first thing to know is that, well, the pressure here will be independent on the horizontal position in the fluid here. Why is that? It's because let's suppose that the pressure here is larger than the pressure here, and we have a small volume of liquid here. Well, it will be pushed in this direction. So that would not work. It wouldn't be an hydrostatic situation. Okay. The other thing we need to know is, well, okay, here we have the air bubble. So how do we treat that? What's happening in there? Now you have to think a bit. Well, an air bubble, let's say we can consider it as being an ideal gas. Could work, doesn't have to be ideal, or maybe not. We'll think about it later. Let's say it's an ideal gas. And it's in there, and when we move the air bubble around, well, we see that its volume cannot change. And of course, we presuppose that the temperature doesn't change. We're just in a room and we just move it around. It's an isothermal process. So if we think about Gases, we know that when the volume doesn't change, the quantity of gas doesn't change, and the temperature doesn't change, well, the pressure inside the air bubble will not change, whatever it is. Okay, so given all this, we can say, well, first, is there pressure in there? Is this the pressure in there larger than the atmospheric pressure? That's a good question. Well, it probably is, because you know that the pressure here is equal to the pressure there. And since the water column is smaller, well, there's got to be a force that pushes on the surface so that the pressures are the same. And how can we basically do that in a more formal manner? Well, the way to do it is to do a force diagram. Here, well, we would put the forces on the objects themselves, but then that would be very cluttered and very difficult to see. So what I'll do is I will say that I will just put forces on the side here. So here what we have is let's say for a unit area here, we have a force of mg. Well, the mass here is equal to the density times the height. So we have a certain height here. We'd call it h1 times the area along the water column. So we suppose we have a column of a given constant cross-sectional area. We just look at the force. So if the total force due to gravity is rho h1a, and this should be equal to p1a. So basically the normal force here at the bottom of the container, which is equal to P1A, and we can isolate P1 equals to rho H1. So that's the first side here. The second side, well, we have the same. So what we have here, we'd call it this one M1. So we do the same. We isolate a column of liquid. We can take actually the old cross section of the tube and we isolate this column here. And the force due to gravity is simply the mass of this column times g, the gravitational acceleration. And here, well, there is some pressure here in the gas, we call it P gas, that also pushes on the water column from above with the force P gas times the area. So we can do the same type of calculations here, and we see that we'd call this one P1 prime. P1 prime is equal to, well, basically the force here that will balance the total force due to this column of liquid and gas is equal, well, by the same calculations we get rho H2, but plus a certain term given by the pressure of the gas. So by thinking about this systematically, by doing a force diagram and using the basic principles that govern the behavior of fluids, we came up with this. And of course, we know that P1 prime must be equal to P1. So we get that these two are equal. Okay, now we go to the second setup. Well, I won't do all the calculations and show all the forces because it's exactly the same. But instead of having a certain height, h2 here, or maybe I should call it H1 prime. Let's call it H1 prime. It's going to make things much easier after. Then we have a different H2 here. We have a different H2 prime. And here we have the same pressure. We knew that it was the same pressure. So we know that P2 will be equal, well, to the same thing. The density times the height, which is H2, plus the same term due to the pressure of the gas, which doesn't change. And now let's compare these two. Is P2 larger than P1 or P1 prime, which are the same? Or is it smaller, or is it equal? Well, if we compare these things, we see that the term P, pressure of the gas, remains the same. And we have the term with the density, which is the same. The density of the water is the same in the two situations. And we're left with H1 prime and H2. And which one is larger? Well, we see that H1 prime here is smaller than H2, which means that P2 is larger than P1, which is our surprising result. And now that we've done all the calculations and we've done things from first principles, we could try to understand physically what's happening. So what's happening is that this gas here has been compressed and it exerts a certain force. And the force that the gas exerts on the water column will be independent of its position in the water column. Why is that the case? It's because its volume is the same, the quantity of gas is the same, the temperature is the same, which means that the pressure in the gas will be the same, whether it's here, or you can even say that in the middle, when you're moving it around, you have a certain volume of gas here, the pressure will be exactly the same, it won't change. So here, we can say that, well, okay, if the pressure is the same, this thing acts like something to compress the water column, and here the pressure is large enough to compensate, let's say, for a water column of that height in between the two. So basically the pressure here is equal to the pressure of this water column, let's call it H3. So basically when you get here, you have exactly the same situation you would have as if you would add H3 here over. That's what it does. The pressure here has the same effect than the water column of the 8H3. And of course, if we add that, we see that the pressure here will be much larger than the pressure here because of this. We can replace basically this volume of gas with the water column of height H3. And that's it for today.